Okay. Yeah. So this is your function y equals to f of x, and then assume that you have 2 points here. For example, let us have it here. Starting point is point, say, A. And then, for example, here you have point B. Yes. And then let me just draw these lines. You are interested in the area which is enclosed between these two vertical lines and the graph of the function and the x-axis. So you are somehow interested in calculating this area. Yes? So it is enclosed by two vertical lines, the graph of the function and the x-axis. Yes, so this is our goal, to find a way to calculate this. So if we want to do this, one idea is to start approximating this area by the sum of the areas of rectangles. Okay, so what does it mean? For example, I will subdivide my interval. So this is my interval from A to B. I partition it into several pieces. So for example, in this case, so let me call this one x1, and let me call this one x2, and this one x3, x4, and then x5. For consistency, usually people call the first one x node or x0, and here the last one, we call it here in this case x6. Yes, so it means that I have one single interval in the beginning, but I partitioned my interval into 1, 2, 3, 4, 5, 6 subintervals. Okay, and then what I do, I actually draw vertical lines from each one of these. So I can draw it solid line. So I can do this, and then this one, and then this one. Okay. So I have now 6 subintervals, and on each interval here, for example, only consider this graph which is on this subinterval. Choose the minimum value of your function, say here, and complete your rectangle. Okay, so I will do that. And do the same thing for the next interval. So the next interval, if you see it is here, this is the minimum value of your function on that interval. So you complete the rectangle here as well. And you do the same thing here. And you do the same thing on the next interval. And then you do the same thing on the next interval. And finally the last one. Yes. And now if I ask you, can you calculate these areas? I think the answer is not hard, yes? We can calculate the area here. We can also calculate the area here. We can calculate the area of each one of these rectangles, yes? And if I add them up, the area that you get is fairly close to the area that you were supposed to calculate. Yes, of course there are some deviations. So this means that, you know, if I start adding the areas of these rectangles, I will not definitely get exactly what I need, because, for example, I am not considering this part which I need to consider. I'm not considering this part. I'm not considering this part. So these parts I'm not considering. So this clearly, the total area of these rectangles is less than the area that I'm supposed to calculate, but approximately it is a good approximation. It's better than nothing. So yeah, we can have some ideas here. Okay, now let us try to understand how we can calculate these things. Okay, so if I ask you what is the area here, what is your answer? How should I calculate this area? I need to find the height of that rectangle. I need to know the width of the rectangle, and then I multiply it. Yes? If I ask you what is the width, how do you answer? No, x1 minus a. But what is x1? So the best answer is a is given to you, b is given. If you calculate b minus a, what do you get? You get the total length. In this case, how many subintervals I have? 6. So I divide this by 6. This becomes the length of each one of these parts that you see. Do you agree? Yes? So this is the calculation of that one. So let me just write that. In our case, each one of these lengths is called delta x. All of them are the same. So I call them delta x, all of them. If I ask you what is delta x, what is your answer? In this case, delta x is b minus a divided by 6. Yes? But can you tell me what happens in general if I have n subpartitions? Instead of dividing by 6, I divide by n. So let us try to understand that, but I want to write everything in the general form. So in general, I divide by n. If someone asks you what is n, you would say that n is the number of partitions that I made myself. Yes? Okay, so this is delta x. Now, if I, for example, if I ask you what is a is just x naught. But if I ask you what is x1, do you agree that x1 is xa plus how many delta x's? Here, x1. I start from a, and this length is delta x, so I go delta x to the right. So it becomes a plus delta x. Do you agree? This is x1. Can you tell me what is x2?
Could you say it's a plus 2
2 delta x, exactly. That's, I want you to understand what is going. I want you to see the patterns. I will clean them up and then put them next to each other. So hopefully you agree. If I ask you what is x3, do you agree? I start from a, I want to reach to x3. How many delta x's I have? I have 3 delta x's. So I add 3 delta x to a, and I will reach to x3. So this is a plus 3 delta x. Okay, so in general, if I ask you x number k, can you tell me what is the general formula here? Yes?
A plus
k times delta x. So this is in general. Yes? So if you don't mind, let me just clean them up. We don't need them anymore. So that is my xk. Okay, now can you tell me, for example, what is the area number 1? The area number 1, I mean the area of the first rectangle. If I ask you to write a formula for the area of the first rectangle, what do you write? You need to calculate the height and then multiply it by the width. The width is clear. How much is that? It's delta x. Yes? So the area is equal to, I put a delta x here, and I have to multiply it by the height. But what is the height? I want you to express it in terms of what we have. I give you the function, f of x is known to you, I give you a, I give you b, and I want you to calculate a1 for me. You would say that, okay, I put the b and a that you gave to me in this formula, I find delta x, this is the width of my rectangle, and then I need to find the height of this rectangle in this particular case. How do you calculate that? Yes, Casimir? Which x? I am talking about a1. a1 is only this one. No, a, which is x naught in this case. Do you agree? Because this is the height. So if I want to know that y, this is the y coordinate of this point, yes? If I ask you how much is this, you will tell me that, okay, the x coordinate is a, I feed it into the function, what I get is the height of this rectangle. Is that right? So this is just f of a. But instead of f of a, to be consistent, I write f of x naught, yes? This is a1. Okay, if I ask you what is a2, what is your answer? a2 is the area of the next rectangle here. In this case, how do you write it? What is the width again? It's delta x. So I put a delta x here. Yes? And what is the height in this case?
x1.
F of x1. Everyone agrees or not? Yes? So that's f of x1. Okay, now can you tell me if I continue this pattern? By the way, what is the last, how many rectangles do I have? In this case, I have 6 rectangles, yes? 1, 2, 3, 4, 5, 6. But in general, how many rectangles I have? N rectangles. So I will continue until I reach to a n. So what is the answer to this one? Definitely you agree with me that you have a delta x there. But what should I write for this particular form of function? Yes? F of x n minus 1. Do you agree?
Why is it -1?
Because here, that is the pattern. When you have 1 here, the index here is 0. When you have 2, the index is 1. So it is clear when I have n, the index becomes n minus 1. Yes? Okay, now the total area of the rectangles is what? The total area is equal to what? Is equal to sum of all these numbers, yes? So which is f of x node delta x plus f of x 1 delta x up to f of x sub n minus 1 delta x. Yes? But I can write this as in the form of sigma. Of course, it doesn't matter, but sigma helps me to write it more compactly. So can you write this for me in the form of a sigma? So this is sigma. So how should I write? In all these terms, what is in common? Delta x is in common, repeating itself all the time. So I put a delta x here. But what should I write for f? I can, what should I write? Yeah? Because you know that a sigma needs a counter. For example, let us choose a letter for the counter. So let us say k. Okay? And here I write what? I write x sub k, but what is the lowest value of k is 0, then k becomes 1, k goes up to n minus 1. Yes, so this becomes k is equal to 1 up to n minus 1. So this is the formula that you get for the area of is the total area of these rectangles. Okay, but if I am interested in calculating the area, so let me call A for the area that we are supposed to calculate. Do you remember? I want to calculate the whole area below this curve and limited by these two vertical lines and the x-axis. So let us call that area A. I cannot say A is equal to this sum. Do you agree? They are not exactly the same. But it is not that ridiculous if I say this is approximately equal to that sum. Yes? I hope that you agree with me. This is reasonable to say that this is approximation. But of course, whenever approximation comes in, we have some errors. Approximations are good if the errors are small. Approximations are bad if the errors are big. But the whole point of this process is that I can make the error as small as I want to. Yes? But the price that I have to pay is to do what? Can you feel it? That's the only point of discussing this. So you see, in this case, I have 6 rectangles. If I ask you how much error I make in this approximation, you can say the sum of these areas, the total sum of these highlighted lines, are the errors that I am making. Yes? So if I ask you how can I make this error smaller, what do you answer? Yes?
Making more rectangles.
Make more rectangles. Is that clear? I just want you to intuitively feel that if instead of dividing my interval into 6 subintervals, if I divide it into 10 subintervals, yes, I have a smaller, each one of these. So for example, if I divide this by 2, okay, then I have one rectangle here. So I also make still errors, but these two errors is smaller than the previous error. So that's the whole point here. So it means that hopefully I could make this plausible for you, that if you want to calculate the area, what do you do in principle? If I make 1,000 rectangles, the approximation is better. If I make it 1 million rectangles, the approximation is even better. But if you are a perfectionist, what do you prefer? Yeah, you make it infinitely many. But of course, being perfectionist is not probably a good idea in this world, because world is not perfect. And the problem is, there is one simple problem there. What's that? Of course, I hope that you agree with me. The ideal thing is to make it infinitely many rectangles, but practically it is not possible in this world, because infinitely many rectangles needs infinitely many time. But that was, by the way, very interesting that this works. Okay, so let us see how it works. Okay, so this I will take that, okay, the A is the limit of this sum. K goes from 1 to n minus 1, f x sub k delta x if n goes to infinity. I didn't, by the way, I didn't prove this formula for you. I made this formula seems plausible. Okay, and that's what we can do. By the way, the definition of the area now becomes this. Okay, so we are changing the definition, but hopefully you agree with me. This is not, this is completely reasonable to get this limit to be the area. The only downside about this formula is if it is practically possible or not. Yes, because how can I divide it into infinitely many rectangles? Even though this example that I want to bring up is not in the book, I want you to see it once at least, that this idea can really sometimes work. And what I will do, I want to bring an example that you already know the answer, and I want you to use this formula to find the answer to see if they match. Okay? So at least understand that this formula sometimes can work. Yes? Let us try to do that. Okay, so let me take this formula with me to the next page. Hopefully it will work somehow. Okay, so copy, we go to the next page, and then let us put it here. Okay, so how should I make it more reasonable for you? So let me just start with a very simple example that you already know the answer from simple geometry, but you pretend for the moment that you don't know, okay? You want to solve that. Okay, so I will take this very famous and simple line, the bisector here. So let me just take it y to be equal to x. Of course, this will also continue from this side, but I don't care about that. I want to calculate the area below this line, which starts from, say, 0 up to, say, let me make it, let us make it, for example, 2, yes? So let me take this one to be 1, exaggerate a little bit so that it is more visible, and then here 2. Okay, and then I draw a vertical line here. I was so unlucky. Okay, and then I have to continue that one as well. Okay. So my goal is to calculate this area. This is 0 line. This is x equals to 2. This is the x-axis, and this is the graph of your function. Of course, you already know the answer. Yes, what the answer is, by the way? What is the area? Yeah, because this is a right angle triangle, so this length is 2. By the way, how much is this length? It's also 2, because y is equal to x. So this is also 2. And if I ask you what is the area is, because this is a right angle triangle, so this is just 2 times 2 divided by 2, which is 2. Yes, so we already know that the area is 2 times 2 divided by 2, which is 2 area units. So we already know. But let us try to use this formula to see if we get the same thing. Okay, so do you remember what is the formula? So the formula is this. Okay, first of all, can you tell me what is delta x in this case? Do you remember the formula for delta x? The delta x was b minus a over n. What is b in this problem? 2. What is a in this problem? 0. Then divided by n. So this is simply delta x is equal to 2 over n. Let us keep it. Okay, but then what do I need? I need x sub k. Do you remember what was the formula of x sub k? Let me just go back here so you see it here. X sub k is a plus k times delta x. Okay, I go to the next page, but remember this in your head. Okay, so let me write x sub k. X sub k was a plus k times delta x. Okay, what is a in this problem? 0. K is just simply k, but I just calculated delta x to be 2 over n. Do you agree? So what happens? X sub k becomes 2 over n times k. Okay, tell me, is that understandable what I'm doing? This is x sub k. But here, what is my function? If I ask you to write the formula for your function, the green line, what is that? F of x is equal to x. Now I want to calculate, according to this rule, I want to calculate what? F of xk minus, f of xk. Okay, if f of x is x, tell me, what is f of xk? It is x, k. Yes, is that understandable? Okay, but what is xk? We just calculate that. It is 2 over n times k. Everything is ready. So if you don't mind, let me just write the sigma part for the time being. After I calculated the sigma, in order to solve the problem, I have to take the limit. So first, I concentrate on calculating this sum. Okay? So the sum of x sub k delta x, k goes from 1 to n minus 1, is equal to sigma. Instead of f of x sub k, I can put this in. So this becomes 2 over n times k. And instead of delta x, you see, I can put 2 over n in. And what are the limits? K is 1 up to n minus 1. So I repeat those. K goes from 1 up to n minus 1. If you don't mind, let me just simplify this a little bit algebraically. So this 2 multiplied by 2 is 4. This n multiplied by n is n squared. So I get 4 over n squared, and then I have a k. But k goes from 1 to n minus 1. Yes? Okay, so because some of you don't know how to work with sigmas, if you don't mind, let me open up the sigma. It is easier for you. Okay, can you tell me what is the first term in this sigma? Do you know how to expand sigma? You need to replace k with the first number, you need to replace k with the second number and add them up. So what's the first term?
4 over n squared.
4 over n squared. Why? Because you replaced k with 1. If you don't mind, let me just write 1 here. Can you tell me what is the next term?
8 over n squared.
Don't write 8. I want to keep the pattern. Yeah, right, it is 8. But let us write 4 over n squared times 2. And this will continue until the last term. What is the last term?
N minus
4 over n squared. The last term is n minus 1. Okay, this is my sum. Okay, now can you propose any way for me to simplify this sum? By the way, this is a very important thing. This is not always possible. I want to get rid of these 3 dots. Be careful. I want to find a formula which is called a closed formula. If you see this, It means write something equal to this expression without having these three dots. That is called a closed formula. So, and by the way, it is not always possible. This is not always possible that whatever you write here, I can get rid of those three dots. But this is so simple that you can really do that. Can you propose me a way how to do it? It's exactly at your the right level. And the reason, you remember, Gustav, you told me 8. I told you intentionally I want to keep the pattern. There was a reason that I want to keep the pattern to do what? Yes?
Is this not a geometric theorem?
No, not geometric. Yes?
I would just start off by deflecting.
Yes, and that was the reason I told you that don't break up things. So I factor what out? 4 over n squared out. And then I have a pair of brackets open. So what is left for me in the pair of brackets? From the first one, 1 is left. From the second one, 2 is left. But this will continue until the very last, which is n minus 1. Agree?
Yes.
Okay, but hopefully, I mean, when you already have Math 5, this should be very famous sum for you. I am adding numbers 1, 2, 3. In Math 5, we also had that when we were talking about arithmetic progression. This is not geometric progression, that's arithmetic progression. Yes? So, and yeah, you need to you remember, let me write the formula here for you. So this is usually the formula people use. 1 plus, I don't know, do you have it in mind?
No.
N times n plus 1 divided by 2. So that is the formula in this case. But in this case, we have a slightly different one. We don't go up to n, we go up to n minus 1. So wherever I see n, I replace it with n minus 1. So let us continue a little bit this fun calculation, yes? So you are excited, yes, aren't you? Yeah, okay, good. Okay, so what should I do? Can you tell me what should I write here? I replace every n here with n minus 1. Of course, this becomes n minus 1, but the next one becomes n. So this becomes n minus 1 times n, and I have a division by 2. And then what happens here now? One of these n's, you see, and one of these n's are cancelled. And these 2 and that 4 are simplified. So what is left for me? I am left with 2 times n minus 1, and what is left in the denominator is just simply n. Do you agree? Okay, and if you don't mind, let me write it in this way. So I write it 2, and I write n over n minus 1 over n. The reason is that because the problem is not finished yet, I want to calculate the limit as well. So you see what happens? This becomes 2 times 1 minus 1 over n. Yeah, is that clear? So this is what I get for this sigma if I have n rectangles. But I want to have infinitely many rectangles. So the area is equal to what? Is equal to the limit of this sum when n goes to infinity. So what's the answer to this limit now?
2.
2. Why? Because 1 over n goes to 0, and then the limit becomes 2. And that is in total agreement with what you had before. Okay? So I just want you to see that sometimes it is possible even in practice. But let us review what is the hard part. So if I ask you what is the hard part of this calculation, can you tell me which part is the hard part? Not because it is lengthy, technically hard part. Yes?
Figuring out that you need arithmetic progression.
Not exactly what, might be you are right, but I don't know what is your opinion. I mean, if I ask you which part of this might really change, because you know that this, I chose a very simple function here, probably the simplest possible function after being a constant function, yes? Okay, first of all, even for this very simple function, you see the calculation is more or less lengthy. And now, if I ask you what is the hard part is this part, yes? that I was able to find a closed formula. In the middle, when I discussed this, I told you that that is not always possible. Yes, for example, can you feel what will happen if instead of having this function, I write something here and then I raise it? Assume that your function is a square root of x. It's also not a complicated function, by the way. Square root of x is a very famous function. But how this will be affected? Can you see how the calculation will be affected? I hope that you agree this will not be affected, because this is depending on b and a, not on the function. Yes, this will not be affected. This will not be affected. What will be affected if I change my function from x to square root of x? Here, yes? Because here it was f of x equals to x. Now it will be f of x equals to square root of x. And now if instead of having f of x sub k is equal to x sub k itself, it becomes a square root of sub k, x sub k. And this square root will be translated actually here. It becomes a square root of 2 over n square root, this one. Yes, it becomes that. So instead of having these numbers, I will have a square root of 1, a square root of 2, up to a square root of n minus 1. And there is no formula for this. There is no closed formula that I can write it without those dots. You see, here the 3 dots are gone. This expression you see is equal to this expression without having these 3 dots. So you see that even if I change the problem slightly from just a simple function x to function the square root of x, which is not complicated, then unfortunately it is really a dead end. Even though it is still plausible, but the bad point is that it does not work. I want you to feel that. Do you understand that? Okay, yes?
Is it not possible to use mathematical induction to get rid of the dot dot dot?
No, that's not possible always. First of all, the bad point about mathematical induction, as I told you before, you need to know the formula and then prove it. Here we don't need, we need to find a way to find the answer. Yes, yes, of course, if someone gives you the final answer, you can prove it. But that is not practically important for us, because we want to calculate all these kinds of sums. And my message to you is that it is not always possible. If the function is slightly even more complicated, there is no hope that we can find a closed formula for any kind of these formulas with dots. Yes?
How did you determine that 1, 2, 3 would be square root?
Yeah, because here, if the function is a square root of x, instead of having f of x sub k, you will have a square root of x sub k, but this becomes a square root of 2 over nk. And when I put it in the sigma, k is 1, k is 2, so I will have a square root of 1, I will have a square root of 2, a square root of 3, etc.
Yes, and even the 4 over n squared.
That will also change.
Yeah,
that will be changed to the square root of 2 over n. Even the problem becomes hard. But that is not hard because I factor it out. The hard part is that sum part. That's why I focused on that sum part. But you're right.
And why is that hard to find the sum?
I cannot say why it is hard because nobody found that. Actually, we will find this sum by an direct method. There is no formula for that. Yeah. Okay, any questions? So the lesson from this calculation is that, first of all, it is sometimes lengthy, even for the simplest possible functions, and sometimes it is really impossible. Okay? Is that clear? Now, the genius of Newton actually and Leibniz help us to calculate the problem. And now this is the connection between primitive function and area, which was not clear before. And that is why we study finding primitive functions. Before this, it was a little bit of mathematical curiosity to reverse engineering the problem. But here, what Newton said is that ask yourself about a primitive function of your function. What is a primitive function for x?
2x.
No, a primitive function. X squared divided by 2. So do you agree? X squared divided by 2 is a primitive function. Are you with me? Yes? This is the simplest possible. Okay? Okay, and then what you are supposed to do, you put this final number there. What do you get? 2. You put the initial number there, you get 0, and subtract them, it becomes 2. So that is Newton's method. So Newton's actually discovered that instead of doing this lengthy thing, ask yourself if you can find a primitive function for your function. If you could find that, then the rest of it is very straightforward. So what you do, you actually calculate the value of that primitive function at the end value. You calculate the value of the primitive function at the initial value and subtract them. Is that clear? So that is the whole point of this lesson. I just want you to understand. Yes.
What if the function is discontinuous?
Pardon?
What if the function is discontinuous?
Now, discontinuity and stuff like that, it becomes a little bit beyond the scope of high school.
Oh, okay.
Yeah.
Because I was thinking that it wouldn't work.
No, but those are plausible questions. But I'm afraid I will not be able to answer them right away here. So is that clear? Yes.
And one last. What if you have a more complex function like an elliptic curve?
Are you starting bringing anchors for me again? Yes. Last session you brought many logarithms for me. Yeah, okay. So anyway, so I hope that you understand this. Yes. Okay. So let us see how it works. By the way, it is a good idea if we go to GeoGebra. Let me see how can I do it. Okay, so let me also go to GeoGebra. At least you can see something. I think so. Here, what I used is called a lower sum. Yes. Let me go back to. So you see here, if I go back, this sum that I wrote here for you is called a lower sum. Yes. Why it is called a lower sum? Because do you remember what I did? I found the minimum value to complete my rectangles. But you can also have an upper sum. Okay. What do I mean by an upper sum here? I mean instead of, so here in the first one, instead of taking the minimum and to complete my rectangle, I take the maximum and complete my rectangle. Yes. Of course, in that case, I will go beyond the area that I need. I get a little bit more. But hopefully you agree with me, by sending the number of rectangles to infinity, I will get a better and better result in that case. So one of them, if you concentrate on making the minimum rectangle, it's called a lower sum. If you start your calculation by maximum value of the function on each interval, it becomes an upper sum. Okay, so let us now go back to GeoGebra. Okay, so here I think there is some instruction here. So lower, yes, there is a lower sum. So here, let me make it a little bit here. So my function here was just simply x. And then what was my starting point? Was 0. What was my end point? What was that? It was 2. And let us, I don't know, how many rectangles do you want? Let us keep it 2 for the time being. Okay, that's not a good idea. But let me also draw the graph so that you can see it. Y is equal to x. Yes, that's your graph. So do you see that I have 2 rectangles? By the way, one rectangle is degenerate, yes?
Yes.
It has, so this is just because the minimum value is 0 here. And the minimum value here is 1. Okay? So now let me make this rectangle a little bit more. So the number of rectangles, let me make it 4. And then let us see what happens, yes? So, and this 1.1 is, by the way, the sum of the areas of the rectangles. Do you know what was the correct answer for this area? It was 2. So it shows that if you choose only 4 rectangles, one rectangle is here you cannot see because it is degenerate. And these 3 rectangles. The sum of the areas of these 3 rectangles is 1.5. But what is the value of the area is 2. So we are 0 point away off. Okay, so now let me increase this to for example, 8. Okay, what do you get about 1.5? What will happen to 1.5, do you think? It will increase to getting closer to 2, yes? So let us just do that. And then yes, so it is now 1.8, okay? So you see that the sum of the areas is now closer to 2. And now, I don't know, let us have some fun. So make it 100. It's already a little bit like a continuum, yes? Yeah, if I zoom out, yes. Of course, if I zoom in, you really don't see the difference, yes? But if I zoom out, you can still see that there are some deviations, yes?
Yes.
Yes, if I increase, you see that there are some very little tiny parts there, yes? Yes, and this is already 2, by the way. If I want to see if it is not 2, I have to go and change the setting, yes?
Yes.
This is 1 decimal place. Let me make it 15 decimal places. Okay, so you see it is not 2. It's 1.98. And you see the deviations. Can you see there? Is deviations. It's very obvious. Yes? But now, who cares? Yes? The hard work is with GeoGebra. Let us increase it to 1000. Okay? Yeah. I hope that you feel that this is really a good approximation. So, and the number is still not 2 because, of course, 1000, even though it is big number here, but it is nothing compared to infinitely many. Yes? Okay, and still, if you don't believe, probably if we zoom in, you can still see the deviation. Yeah, very nice, by the way. Yeah, so you can see still there are deviations, but the deviations are much smaller. So is that clear?
Is there a function of how fast it reaches to 2? Or how fast it...
Yeah, we can discuss about these things, but these are
What is it called? It's like...
the speed of convergence, the rate of convergence. Okay, so is that clear now? Okay, but and so you found a relation between actually the area and this sum. So this sum is called the integral. Okay, so let us go back to. Okay, so here what we want to write is that let us have these things. I have a function. I have an interval. F is continuous on this interval. Yes. And then in that case, we have this symbol, integral of the function f of x. You put d of x here, and you write a to b. This is called the integrand. Let me write all these things here. So this is called the integrand. Your function has a name. It's called the integrand. Okay, so a is called the lower limit. Oops. And then b is called the upper limit. And dx here, which is not that important for your lesson, is called the differential of x. If you want to get a feeling, I would say that dx is approximately the same as delta x. Or if I want to write it more precisely, you might say that dx is the delta x when the limit n goes to infinity. I mean, it's the infinitesimal. Of course, this is 0. It's not a good way to write this in this form, but I want you to get the feeling. dx is the infinitesimal version of delta x. I cannot elaborate more than this here. But you always have dx in your integral. By the way, the integral sign is in a stretched s. Yes, because when you calculate an integral, you are calculating a sum. Okay, so integral means a sum. Okay, how we define this? Exactly how we defined it before. So if I ask you, what is the definition of this symbol in mathematics? whenever you see this symbol, it means limit of the sigma f of x sub k delta x. K goes from 1 to n minus 1. It doesn't matter if I write it n, because eventually I want to send n to infinity. So there is no difference between n or n minus 1. So this is the definition of integral. But I told you that using this definition, even though that was the motivating part, it is not practically useful. To calculate this, we use the Newton's formula. Okay? So now, if I want to express Newton's formula, by the way, this is called the second fundamental theorem of integral calculus. The second. So if I want to write the formula here for you, the formula is written in this form. If you want to calculate, let me change the color here. If you want to calculate integral of a given function from a number a to a number b, what you do, you ask yourself about finding a primitive function for your integrand, and usually people write it like this, from a to b, and then what do I mean by this symbol? It means f of b, f of a, subtracting. Yes? So if I ask you what is the meaning of this, it tells you that if you want to calculate an integral, ask yourself about a primitive function. A primitive function is enough. You find a primitive function for f of x. You replace x with the upper limit. You replace x with the lower limit. You get two numbers. You subtract them in this order. The number that you get is the number for this integral, is the value of this integral. Yes? So you don't need at all to use this formula, especially for this course. Is that clear? Okay, for example, let me solve some problems for you here. So example, determine the following. We can also say compute, because the integral will be a number at the end. Determine the following integrals. So number one, let me make it very, very simple for the time being. So integral from, say, 1 to 3, I have 2x squared plus 3 dx. So I want to calculate this. So look here, this is your function. In order to calculate this integral, the first thing that you need to ask yourself is, how can I calculate a primitive function for this? Okay, so but that is easy. What is a primitive function? Do you know? A primitive function of this part is, I hope that you remember the formulas. I'm lazy to write the formulas again. So what's the formula here? 2 goes out, and what is a primitive function for x squared? x3 divided by 3. Yes? So this is 2 times x to the power of 3 divided by 3. And tell me, what is a primitive function for 3? A primitive function for 3 means a function whose derivative is 3. What that function is? 3x. Okay, And if you don't mind, let me simplify it. By the way, the way you write is important. So you have to put a pair of brackets around. Okay, you are not allowed to repeat this. Yes, because you already did the primitive function part, but then you have to replace it with the vertical line, and then from 1 to 2. This is the way that you have to write it. Yes, please.
I have two questions. Why did you put plus C?
Okay, if I put plus C, it doesn't matter because plus C appears for the upper limit and the lower limit, they will be cancelled out.
Yeah.
So yeah,
Why is it 1 to 2 and not?
no, you're right. That is my mistake. Yes, to 3. Okay, and then what you do, I do like this. I hope that, yeah, it depends on you what you want to do, but what I want to do, I just do it in 2 different steps. Every appearance of x, I replace it with the upper limit. So what happens? It becomes 2 times 3 to the power of 3 divided by 3 plus 3 times 3, and I calculate it patiently. So what's the answer? What's the answer? In total? Yeah, 27. 9, and that is also 18, yes? And now I do the same thing. I replace every appearance of x with the lower limit. So this becomes 2 times 1 to the power of 3 over 3 plus 3 times 1. If I calculate that, it is just 2 over 3 plus 3. So if it becomes 11 over 3. And now I go back to horizontal line. What I got above, I write it, minus what I got below is 1 over 3. So this becomes 70 over 3. Yes, so that is the value. By the way, that's also good to learn because in national exam you need to be able to use this application here. So let us go back. Oh, unfortunately I recorded everything wrong. Yeah, so it is. Yeah, so there are many things that I have to consider anyway. But you can see my voice with GeoGebra scene. Okay. Now I go to GeoGebra, then I switch the scene to a server. Yes. Okay. I don't know what I can do with the Natura students then.
You can take the voice recording and then put some pictures of the
No, I can do a lot of things, but I'm too lazy to do that.
But they're not here. It's their fault.
Just tell them to review this.
Okay, we can do something. I can do something similar when you are not here.
No.
It would be fair, yes?
No.
Okay, so let us now go back to, I'm confused about all these buttons here. So anyway, so let us go to GeoGebra and learn how to calculate this. So I think we need to go to CAS view here. Okay, so there is an integral sign here. Let us use this. Okay, so how should I do that then? So let me write my function. So what is my function? F of x is equal to, so let me write g of x because this has already been repeated. G of x is equal to what? It is 2x to the power of 2 plus 3. Yes? So if I want to integrate that, so I don't know, how should I integrate it then? Okay, so let me write integral. It's easier. Yes, integral of function variable. So I use this. So I write 2x to the power of 2, and then I go plus 3, and my starting value is 1. My
Equal to.
okay, thank you. So this is plus, yes?
Yes.
And then I jump to this one. It is 3.
Yes.
Okay, and unfortunately I don't know why it gives me, there is no way that I can find the exact value. That's also very strange. But I think it is correct, yes? 70 over 3 is 23.33, etc. Okay, so that's also possible, but you probably can figure out how to use the integral sign. It was easier for me to write it as like a quote here. Okay, so I go back to here now. Okay, let me ask you to calculate one more, number 2. So for example, let me write this. Integral from e to e squared, then I have 1 2 over x dx. So I want to calculate the exact value of this. So how should I do that? So here, this is your integrand. You need to find a primitive function for 2 over x. What is that? 2 ln of x, yes? So this becomes just simply 2 ln of x, but I have to write this vertical line. It goes from e to e squared. What does it mean? I have to replace every x with e squared, but this is possible to calculate. How? I move this 2 to the back, so it becomes 4 ln of e, but what is ln of e? 1, so this becomes 4. And then I go and do the same thing with the lower limit, but ln of e is just simply 1, so this is 2 times 1, which is 2. Then I go back to horizontal line, I got 4 minus 2. So the final exact answer is 2. Yes?
Are you recording this time?
Yes, this time, yes. Exceptionally, yes. So here we go to the next one. Let me choose this one from the book and we are done. Because now I will break this into 2 parts. I will teach it later. Okay, let me calculate this one for you. So number 3. So according to the book, we are supposed to calculate integral from 1 to 2. I have 1 plus x over x dx. How should I compute this integral? Yes?
You can rewrite it as 1 over x plus x over x.
Okay, exactly. So we have to do this, but be careful. I am not integrating yet, so I have to keep the integral sign. This is important. Don't mix these things. I am simplifying. So I write 1 over x plus x over x.
Baba,
Yes?
could you not write 1 over x ln of x?
No.
No, sorry, 1 plus x ln x.
No.
Why?
It is not possible to take them. I told you several times, you are not allowed to take the primitive function of the numerator and denominator separately.
No, I mean you take the numerator and then you. Oh, no.
No, there is no way. Yeah. Okay. So then you see that this is important. Remember, I am keeping the integral sign yet. Still, the next step, I will keep the integral sign. Now that everything is ready to find the primitive function, I have to remove the integral sign. What is the primitive function for 1 over x? ln of x. What is the primitive function for 1? It's x. So I have to write this. Then I have to remove. This is a have to. I remove the integral sign and then I write from 1 to 2. So what happens? I have 2 things to do. I have to replace every x with 2. And then you have to keep the exact value. Do not use the calculator unless it is mentioned in the problem. And then you replace every x with 1. In the bottom one, I can simplify more because ln of 1 is 0, so this becomes simply 1. And then I go back to horizontal line, I get ln of 2 plus 2, and then I get 1 below and I subtract them, so the answer is just simply ln of 2 plus 1. I usually prefer to write 1 plus ln of 2, not to mix things. So this is the answer to this integral. And finally, number 4, if you have questions, please let me know. This is number 4. This is also in the book. I'm just using that. So integral This is a trigonometric function. It's very simple, by the way. Yeah. So it's from 0 to 2 pi sine x dx. Okay, so what should I do? I mean, the answer to what should I do is always the same. You need to find a primitive function. So you know that if you are not good in finding primitive functions, then you will be in trouble here as well. So what is a primitive function for sine x? Minus cosine x, exactly. So this becomes minus cosine x, and x goes from 0 to 2 pi. And then what I do, I prefer still go it in that way. This is usually more helpful because I have seen students know how to solve, but they mess up minus signs. So this is minus cosine of 2 pi. What cosine of 2 pi, do you remember, is 1. I have a negative sign, it becomes minus 1. Then I have minus cosine of 0. What is cosine of 0? Again 1, but I have a minus sign, it becomes minus 1. And then I go back to horizontal line. I get minus 1 above, I get minus 1 also below, and I have to subtract them. So what's the answer?
0.
0. Okay, any questions? Okay, so I will not complete this lesson. I just calculated the integrals, but then I will come back and teach you about how to find the areas. It's essentially the same problem, but there are some technicalities that you need to know. Sometimes, by the way, you see that why this integral is 0. Is that possible? Because we told that integral is somehow the area.
Yeah.
And you know that the graph of sine x is not exactly on top of x-axis, that the area is 0.
No, but that's from physics. We know that everything under that line is negative and positive. You add them up.
Yeah, so this I want to discuss a little bit why this is, by the way, indeed the case. So this interpretation that integral is always the area is not the correct thing. It is related to the area in a very close way, but there are some differences that you need to understand as well. So I want to keep the lesson here so that you can practice more, and then we come back to the notion of areas. Any questions? Thank you very much.
Thank you.